Okay, so let's review question 2 from quiz 7. And in this question, it says eggshells are thinner in the summer when the rate of chicken panting is greater. So when a chicken pants, what's happening? Yeah, so they're releasing CO2. Now, is CO2 in this equation anywhere?
Yes.
I don't see CO2. So what does CO2 have to do with this chemical equation? Yeah, so the CO2 is related to the amount of CO3 minus in the reactant side. So if the chicken is panting at a faster rate and CO2 is related to CO3 minus, what's happening then to the carbonate ion? Is it by increased panting or increased rate of breathing, is the CO3 minus increasing or decreasing? Yeah, so as the CO3 minus is removed, in which direction does this reaction shift? Yeah, toward the reactant side, which means that less calcium carbonate is being produced, which means that the eggshells are thinner. And then a lot of you did a very nice job suggesting a remedy for this situation. So what you want to do is house the chickens in a cooler environment. So lower the temperature so they don't breathe as rapidly. While we're at it, let's actually do question 1. So question 1 shows the decomposition of calcium carbonate into calcium oxide or lime and CO2. 2 equilibrium constants are given, 1 at 1,000 degrees, 1 at 848 degrees. Calcium carbonate is the active ingredient in Tums and Rolates. Is it safe to store Tums at room temperature? So for example, if we store Tums at 1,000 degrees Celsius, would we have any calcium carbonate present based on the information we're given? So at 1,000 degrees, would there be any calcium carbonate present? And what number do you want to look at to answer that question? Yeah, if you want to look at the K value, if you look at K, the equilibrium constant at 1,000 degrees is 9.75. So this tells us that is there going to be more reactants present or more products present? Okay, more products. So at 1,000 degrees, does calcium carbonate decompose? It sure does. At 848 degrees, does calcium carbonate decompose? Yes, note here the equilibrium constant is 1. So based on these 2 temperatures and equilibrium constants, is the decomposition of calcium carbonate endothermic or exothermic? And why endothermic? See, because really, the way I ask the questions, either, it's one or the other, so it's easy to guess. But since you guys are scientists and engineers, and you want to do more than just guess, you can just flip a coin. You don't do that. So, why do you think this reaction is endothermic based on the information that you're given?
The colder it is, there's less product, right? So
yeah, so, for example, if you say that this reaction is endothermic, heat is considered a reactant, so as you increase the temperature, in which direction does this reaction shift? And toward the product side. So if it shifts toward the product side as the temperature is increased, does the equilibrium constant increase or decrease? it should. Okay, so you're saying that as the temperature increases, the reaction shifts toward the product side. Does the equilibrium constant increase or decrease? Okay, so you raise the temperature, reaction shifts toward the product side. That means there's more product, which means that the equilibrium constant K is going to be bigger or smaller? It should be bigger. Okay, so at room temperature, we're even lowering the temperature more from 848 degrees to 25 degrees. Is it safe to store calcium carbonate or Tums at room temperature? Yes, it should be, because we would expect the equilibrium constant at room temperature to be bigger than 1 or less than 1. It should be less than 1, quite a bit less than 1 in this case. And actually, this last part here, calculate K at room temperature, we haven't gotten to that yet. So we talk about more about energy and chemical reactions. We can apply thermodynamics to actually calculate the equilibrium constant K at room temperature. So we'll do that in a few weeks, actually after spring break. Okay. Let's do question 3. Sulfuric acid is the acid found in car batteries. What are the major sulfur-containing substances in this solution? Okay, so what is the chemical formula of sulfuric acid? Okay, so it's H2SO4. And what type of substance is H2SO4? It's a covalent compound. It's also an acid. Is it a strong acid or weak acid? Yes, this is a strong acid. That means that if this is a strong acid, what will you see in a sulfuric acid solution? Yes, you see H plus and what else? Now, what type of this is a strong acid, but is it a monoprotic acid or polyprotic acid? Yeah, so how many H's here? There's 2, which means it's a diprotic acid. Okay? So it's going to be H plus. Now, when acids donate protons, it donates it 1 at a time. So it's going to form H plus, and the conjugate base of H2SO4 is HSO4 minus. Okay? Now, HSO4 minus can accept a proton to reform H2SO4, but HSO4 minus can also donate a proton to form H plus, and what's the conjugate base of HSO4 minus? Yes, sulfate. So based on this information, what sulfur-containing substances are in battery acid? Okay, so here's your sulfuric acid solution. So what's going to be in there besides water? I'll put water. Because every time I ask this question, someone always says water is present. So I'll put that in there. Okay, H plus is present. But see, the question still is, what are the major sulfur-containing substances? H plus doesn't contain sulfur. HSO4? HSO4? Anything else? SO4 2 minus? Now, you told me correctly that this is a strong acid. So we expect that strong acid to dissociate completely into its ions. Is HSO4 minus a strong acid? And what table can you use to help you answer that question? Because I'm hoping that you're not sitting at home on the weekends memorizing how strong and weak acids and bases are. Are you really doing that? Really? You mean you don't have anything better to do with your time than to memorize acids and bases?
It's a weak acid.
And Jeff, what table are you looking at to figure that out?
16.2.
Table 16.2? Yeah, so on page 553, table 16.2 shows you the relative strengths of acids and bases. So note that HSO4 minus is considered a weak acid. Actually, we can quantify that by looking up the Ka. So the Ka of HSO4 minus is given in table 16.4, and that's on page 563. Ka for HSO4 minus is 1.3 times 10 to the minus 2. Okay, so that's a weak acid. Okay, so if HSO4 minus is a weak acid, would we expect to see SO4 2 minus in the solution? Why not? Because HSO4 minus is a weak acid. Really, for the most part, we'll see HSO4 minus and H plus and water in this solution. Okay, so we're not going to see any, or just a very small amount of sulfate ion in this sulfuric acid solution. Let's go back a slide and let's do this one. So last Thursday in class, we did question 1. We looked at the titration curve of aspirin. Now, did we finish this one last Thursday? Did we finish all we calculated the pH at the starting point, halfway point, and end point? Did we do all that? You did? That means you're ready for question 2. In question 2, it states 20 milliliters of 0.1 molar phosphoric acid. It is titrated with 0.1 molar sodium hydroxide. Now, you used some phosphoric acid in lab last week to help you prepare buffers. So what you want to do is calculate the pH at the starting point, the halfway points, and end points. Now, here's a new formula. At the first and second end point, pH equals 1/2 pKa1 plus pKa2. Draw the titration curve and show each buffer region. Show each phosphorus compound and the charge at each point. Now, phosphoric acid is a triprotic acid, so what would this titration curve look like? So, again, we'll plot our titration curve pH versus... Okay, so let's do that. So we're going to plot pH versus the volume with base added. Now in question 1, we showed for aspirin as a monoprotic acid, it showed 1 halfway point and 1 end point. For a triprotic acid, how many halfway points and how many end points will you observe? Okay, yes, you see 3. How is the titration curve going to look?
3 ways.
So how does it look? Yeah, so there's 3 endpoints. We see 1 endpoint here, and then we see a second endpoint, and then we see a third endpoint. Okay, so what you want to do is figure out the pH at each endpoint. Okay, so these are 3 endpoints, and each halfway point too. So here's our halfway points. Okay, so we've got a few And then here's the starting point. So here's the pH at the starting point, and then pH at the halfway point, pH at the first end point, the halfway point, second end point, third halfway point, and then the fourth end point. Okay, so this is pH at the third end point. Okay, so we want to figure out the pHs at each point. And before we do that, let's just write down the